that celebration for being recorded. Okay, so let's begin. Now this week I don't like I actually really wanted to do Fibonacci heaps, but you know, like my colleague was like, can you not? So unfortunately, no Fibonacci heaps. Okay, so we'll do graphs instead, and in particular, my colleague did suggest a really good idea which is that we kind of go through like some basic graph tricks that you guys can use. What I mean by this is that sometimes like when you're trying to do algorithm design, for example, you know, like we've taught you guys like how to come up with algorithms, how to cook up like specific like, you know, like like specific techniques like using, for example, let's say greedy or DP. But sometimes like, you know, you can sort of, instead of like modifying algorithms or coming up with like new algorithms, you know, like that there is a possibility for you guys to use like the old algorithms that you learned in 2040, for example, and instead of even like updating those algorithms or like changing those algorithms a bit, sometimes what you can actually do instead is just like change the graph or like change the input. And if you do that, you realize that you can actually solve a lot, like, you know, I wouldn't say a lot more problems, but there are definitely quite a few things that you can end up pulling off. All right. So for the first part of this tutorial, I'm going to show you guys some ways where instead of changing algorithms, we're going to use the same algorithm, but we're going to run them on like different inputs. And I think like based on the previous class, I only have time to do SEC, like this DFS algorithm that solves bridge, articulation point, and SEC after that. And if I somehow magically get that done in time, we'll talk a bit about using MSE to solve this problem that I really like. It's one of my favorite problems. But yeah, so let's begin. Oh, every time my webcam tablet does that. Why is it doing that? Okay, so let's begin. Let's talk about shortest path finding. So if you kind of remember, how we did shortest path finding was that we, you know, like if I for example told you something like, okay, I have a graph and it has positive edges, positively weighted or like non-negatively weighted edges, you know, and it's, let's say for example, a directed graph or whatever, doesn't really matter. Then you would just say, oh, let's just use Dijkstra, right? And Dijkstra would be like v plus e log e time or something, and then you would be like, okay, good. Then if I say, oh yeah, but what if there are negative edges, but, you know, no negative cycles, then you would say, okay, let's just use Bellman-Ford, which is like OV times E time, very good. And then, you know, some of you might say, oh, yeah, but we can topo sort for if the graph is directed acyclic, we can topo sort first, and if we topo sort, then what we will understand from the topo sort is something along the lines of, okay, if we can topo sort it, then if it's a DAG, we can topo sort it and run a one pass Bellman-Ford, right? And in that case, that would take like OV plus E time to find the shortest distances, right? So you should already have like all that under your belt somewhere, roughly. Okay, so what we can try to do is we can try to build on that to solve like maybe some extended versions of these problems. So the first one that I want to give you is something called like it's still shortest path finding, okay, but let's say for now within k edges. Oh, sorry. So what I mean by this is that let's say I want to do shortest path, but I also have this constraint that says I don't want to take too many edges to get to my shortest path. Okay, so this constraint doesn't really care about the edge weights. It really just says something along the lines of, like, for example, if I were to give you a graph that looks like this. Okay, maybe this is like edge weight 1, this is edge weight 1, this is edge weight 20 or something like that, right? Then the shortest path from S to T would of course be 2, right? Because you can just go up this route, right? Go up this node and come back down here. But, you know, like what if I said, okay, I want shortest path within, you know, exactly 1 edge. Okay, in that case, what you should be like, what your algorithm should return is not 2, it should return 20, right? Because even though this is not really the best path that you can take, okay, this is the only way you can reach from S to T with using only exactly like 1 edge. Okay. So this kind of looks like a shortest path problem. I mean, it is a shortest path problem, right? But it's not the one that you guys solve using Dijkstra, for example. And if you try to just say, okay, we're going to try to run Dijkstra using this, and then, you know, like somehow try to solve it that way, like that wouldn't work very well, because first of all, the graph that you gave it, you know, is still the original graph, and the algorithm itself doesn't really have this notion of I'm gonna only do k edges. I mean, there are ways to modify the algorithm, right? So one thing straight off the bat, I'm just gonna make this passing remark, but without me telling you what to do next, right? You guys should actually already be able to solve this. So what I'm trying to say is that if this question came on your midterms, right, you wouldn't need my tutorial, like this tutorial right now, to be able to solve this question, because it's technically a dynamic programming question. So all you actually have to do is formulate this as a recurrence, and you realize something along the lines of shortest path within k edges is actually like shortest path, like, you know, like you can solve all shortest path like problem. Like if you could solve the single source shortest path problem with k minus 1 edges, right, you just need one more step to get like all the shortest path with k edges, right? So it is a dynamic programming problem, like if you formulate the recurrence like that. So you actually don't need what I'm about to tell you. But I think what I'm about to show is pretty deep, and this is not the only problem it solves. There are other problems as well, but you know, just as a passing remark. So what should we do? The cool thing here is that we're not going to actually modify the algorithm. What we're going to do here is we're going to modify the input. Now, you can think of modifying the input as like modifying the algorithm. It's like, okay, I take my Dijkstra algorithm and then I surround it with some code, and you know, now I have a new algorithm. That's kind of like modifying it. Yeah, you can see it that way too. That's fine. Now I'm kind of, this gets messy for complicated graphs really quickly. So let me just use a 3-node graph to illustrate my point. Actually, maybe a 4-node graph, because like maybe it only shows like obviously after 4 nodes. Let's say this is my original graph. Okay. And let's say k here, let's say k, right? Like I want shortest path where k, within k edges where k was equals to, let's say 2. 2 is kind of interesting, I guess. What you want to do is, first of all, you want to copy out the nodes. Okay, so if let's say this was node 1, this is node 2, this is node 3, and this is node 4, okay, make copies. Okay, so if k is equals to 2, I need you to copy it twice. So copy it once, copy it again. Okay, so it should be apparent, but this is node 1, this is node 1, this is node 2, this is node 2, this is node 3, this is 3, this is 4, this is 4. Okay. Okay, now what I need you to do is that if you look at these edges, right, if one is supposed to point to 2 in the original graph, I need you to get the new graph to stop doing that. So you need to remove this edge. And what you need to do instead is point 1 to the next 2. And rinse and repeat this. So 1 points to the next 2, right? And if 2 points to 3 in the original graph, I need you to get rid of it. And now 2 points to the next 3. 2 points to the next 3. Okay, and do this for all the edges. So if like 1 points to 3 in the original graph, get rid of it. Then now 1 points to 3. So you see what I mean? This gets ugly really quickly. But I mean, you know, if you program this in Python or like Java or something, like since the computer has to do it, not you, hopefully the computer doesn't screw up, you know. So 3 points here, and then 3 points here, right? I think 4 points to 1, right? So like get rid of this. Now 4 points to 1, 4 points to 1. I know you can't really make sense of the original graph now, but like, you know, you could, yeah, I don't know. It's very difficult if I don't have a 3D drawing paper, like whatever. But like, it's not as if I can draw in 3D. It looks better in 3D. You can think of them as like the graphs are like laid on top of each other. The edges, instead of staying on the same level, are like moving up one level, that sort of thing. But this is roughly what it should like actually look like. You know, let's just get rid of all these edges, so that I can actually just explain the concept better. So pretend I already have all these edges, right? So pretend that like these edges are like not in the original graph anymore, and they're now you know how to draw them. Let me just not have them, because it'll, you know, not have them explicitly on the screen, because it'll be easier to show you what I'm trying to do. Okay, now what you, okay, so let's just say this is copy 1. So this is copy 1, this is copy 2. So what's the intuition here? The intuition here is that when you make a copy of a graph, right? Okay, if I could somehow find a way to get from my source, right, to some node, let's say this one, right? Let's say that from some node of my source, right? I just take one edge. Like if I can reach here, right? What does it mean? It means that I can reach here in exactly one edge. Okay, and if, for example, there was a way for me to reach from S to this node, taking all the edges that I drew, what that means is that there must have been a way for me to get from node 1 to node 3 in exactly 2 edges. Exactly, all right? Not like less than or equals to, but exactly 2 edges. Okay, so Likewise, if for example, I can find if there is a sequence of edges, like based on the ones that I drew, such that I could get from, let's say, from here to here, right? That means I know that there must be some path, right, in the original graph, which uses exactly two edges, right? So the intuition here is that basically this node kind of quote unquote remembers how many edges you took to get there. Okay, I mean, again, with like all these edges drawn out, right? So I mean, I know the edges aren't on the screen, like you just have to pretend that they're there. Okay. So how does this help us? How this helps us is that if I were to run Dijkstra here now, okay, every time your Dijkstra algorithm takes an edge, right, it doesn't actually visit like the same node, like a node on the same layer as it's supposed, as you know, like as it would. What it would do instead is actually visit, like for example, if it could have taken this node, right, like what the Dijkstra algorithm would do instead is that it would visit the node here, like on the next layer, on the next copy. Right. Likewise, let's say for example the Dijkstra algorithm was already here, and you try to run one more iteration, like it would visit the node here in the next copy. Okay, so what does this mean? This means that now Dijkstra has, like when you run the Dijkstra algorithm on this graph, it sort of says, okay, let's say I have like made let's say two steps away, like one step away from the source, right? If I run another iteration of Dijkstra, it's going to, like, if I'm some node here, if I am at some, let's say some node here, and Dijkstra now like tries to relax all its neighbors, right? All its neighbors are going to be like in the next copy, right? So Dijkstra, like now the Dijkstra doesn't have to remember it. The graph kind of says, okay, look, you know, if you're one step away, you're going to relax neighbors that are all two steps away, right? If you are 0 steps away, you're going to relax all neighbors that are one step away, that sort of thing, right? And if you make k copies of the graph, right, the most that you can do is k steps away from the source, right? So this, like if you copy it once, this allows your Dijkstra to relax one step away, and this allows your Dijkstra, if you make another copy, this allows your Dijkstra to relax 2 steps away from the source, right? So all you have to do is sort of copy out this graph, draw the edges in this manner, and then run Dijkstra. I know, like usually when we cover algorithms, they're a bit more complicated than this, but this is all there is to it, really. So with this, you guys already like this is like a quote unquote new algorithm, which isn't really new. It's just, you know, like I'm just saying, okay, copy out the graphs, copy out the nodes, and then draw the edges this way, and then you just run Dijkstra. Now you've solved shortest path within k edges. No one seems mind blown. but yeah, does everyone get the idea? Because like some people just now weren't in the previous class weren't very confident, like or like were slightly confused about this. But does this make sense to you guys? I'll give you guys like half a minute to think about whether it makes sense. A bit confused how it solves shortest path within k edges, right? Okay, so let's say I want to find the shortest path from single source shortest path from 1 to, okay, let's say for now just like, you know, like not single source shortest path, but let's say from S to, let's say 4, right? And like this is S, so S is 1 and T is 4, right? And I want to find the shortest path from 1 to 4, but only within 2 edges, right? So the only path, well, actually the only shortest path that you can take is the only path that you can actually take is this one. So it has to be quote unquote the shortest, right? But the point is that you could have a very cheap path that somehow, oh no, you can't, because all the edges are positively weighted. Oh no, you can, right? So like you can weight it so that like this guy is 1, 1, 1, and here's like 50 or something, right? Then if you want shortest path without, like, you know, without this restriction, then the shortest path should be 3. But if let's say I restrict you to only use 2 edges, then the shortest path should be 51, right? Okay, so think about the edges that like think about like one, like let's say for example Dijkstra starts here and it enqueues this node, right? So what's going to happen is that it's going to relax some neighbors, but which neighbors does it relax? It doesn't relax 2 and 3 anymore in the original graph, like in you know, as it should have in the original graph, because we made a copy, right? So there's supposed to be like these edges that point out this way, right? So when you relax your neighbors, right, what's going to happen is that the distances to these, like the distance estimates, is going to be relaxed down to from infinity down to, this one's going to be 1, this one's going to be 50, right? And those are actually the only 2 nodes that you're going to see in the queue that have like relaxed distances, right? So now what will Dijkstra do? Which node should Dijkstra look at? Dijkstra should look at this node, right? So if Dijkstra looks at this node and tries to relax its neighbors, what neighbors do you actually have? Well, there's going to be two other edges. One edge points to the next three, and one edge. Oh no, that's the only edge, right? So then what happens here? You have an edge. You have an edge weight of 1. So the distance that's going to be this distance is going to be relaxed from infinity down to 2. But that's fine. I don't really care about that, right? The point is that okay, now you have some distance too, but this guy has no outgoing neighbors. Okay, so this guy's done. Dijkstra's done with it. This guy's done. Dijkstra's done with it. So on and so forth, right? Now this node is not done yet, right? So you pop it from the queue, and then Dijkstra would say, okay, what neighbors do you have, right? And then this guy would say, oh, I have one neighbor. I have neighbor 4, right? So neighbor 4 is here, and it's with edge weight 1 in the original graph. So what distance does what distance is this relaxed to? It's relaxed from infinity down to 51, right? So when you're done running Dijkstra, right, you have like multiple copies of distances for the same node, right? The first copy of the distance tells you how what is the distance from S to T with 0 hops. There should always be infinity. No, I think so. Yeah. What about within 1 hop? If you look at the original graph, right, you can't reach from node 1 to node 4 with 1 hop anyway, right? So that the distance remains at infinity. That makes sense, right? But what about within 2 hops? Within 2 hops, you know that what about exactly 2 hops, right? 2 hops meaning taking exactly 2 edges. So you know that there is exactly one path that does that, right? So like this path here, 50 to 50 plus this 1, so that gives you 51, right? So you look at all these copies of the distances, right? The 0 copy, the 1 copy, the second copy, so on and so forth, and you realize that this is the shortest possible distance you can take to go to T. Does that make sense? You should think of like each copy of the graph, right, as like not just visiting that node, but visiting that node in exactly that many steps, right? So the 0th copy of the graph is like if I'm stepping on this node, right, it means that I've come here from the source node with exactly 0 steps, like using 0 edges, right? If I'm stepping on this node, that's me like arriving at this node after taking exactly 1 edge, right? And if I'm stepping on this node somehow, right, this means that I must have gotten away from the source, right, to this node in exactly using exactly 2 edges. Does that make sense? Cool. Can I ask what proof correctness of this algorithm would look like? Well, okay, so you know that this solves single source short. You know that Dijkstra solves single source shortest path, and if you're allowed to import that proof, right, you would then say, okay, how am I going to prove this algorithm is correct, right? How am I going to prove that this algorithm finds the shortest path within k edges, right? So this is a good question which I didn't answer in the previous group, but anyway, so first of all, you need to argue that the copying does exactly what you wanted to do. So what was the intuition I was trying to convey? Again, it's that if there is some node on some kth copy, right? Let's not use k. Let's use ith copy, right? So like some node on the ith copy, right? When Dijkstra visits that node, you need to argue that it must have taken exactly like I edges to get there, right? You can argue this by induction, right? Like this case is easy. If I made 1 copy, for example, you know that if I visit the node on the first copy, I must have taken exactly 1 edge to get there. Literally by definition of how I've constructed the graph, right? So this really ties into like how you're constructing the graph. And the inductive step is easy, right? Assume that you could do it. Assume that this algorithm works. If you made I-1 copies, if you made an extra copy and drew the edges that way, since all the edges are like pointing out from the I-1 copy to the ith copy, you must have taken exactly I-1 edges to get to the end of like the most recent copy, and then like exactly 1 edge to move to the next copy, right? The ith copy, right? So now the graph does exactly what you wanted to do, right? Which is the intuition I was trying to convey to you. Like if there is a way for you to get from the 0th copy down to some copy here, you must have taken exactly that many edges, right? Then you would just say, since I'm running Dijkstra on this graph, and you know that every node in a specific copy represents exactly how many edges it takes to go to that, right? And Dijkstra correctly finds the shortest distances to that node, right? What that translates to is saying that it must have found the shortest path from from source to that node in exactly that many hops, right? But taking exactly that many edges, right? But I want within, I don't want exactly, right? So what you should do is after you run Dijkstra, you need to find the min, right? So like you go to like all the same copies of distances and you get the minimum. Does that make sense? right? So the reason why you need the minimum, not the last, is because, like, for example, if let's say this edge here wasn't 50, but this edge here was, let's say, something like 0, right? Then the shortest distance, like from 1 to 3, is not going to be 2, right? Because like the distance here, it would still say 2, but the one here, you would say like 0 instead, and this is the one that you should be taking. So you should still have to min across like all the, but that's just like a by definition thing, right? So you just have to take a min across all the distances. Okay. Okay. Looking at the current time, it looks like I will not be able to do the MST question. So I'll give it as an exercise in the Telegram group later. So yeah. Okay. So we're done with this one. Let's do the next one. Okay. Oh, by the way, runtime, you guys can figure it out. Like, so that's another important exercise. Go figure out what the runtime is. It's not v plus e times like log e anymore. That's not the runtime anymore. Okay, what's the next thing that we're supposed to cover? Let's see. Supernodes, right? Okay, this one is pretty easy as well. Okay, this one is like a 2-minute algorithm, honestly. So let's give you another shortest path finding algorithm, shortest path finding problem, right? But now let's say I give you a graph. The graph kind of looks like this. It's kind of frustrating. Like sometimes every time I have to draw a graph, like I need some bare minimum amount of creativity that I don't have. I don't know, maybe something like this. One more node here. Okay, good. So let's say I have a graph that looks like this, right? And right now I have a different problem that I want you to solve. It's still related to shortest path, but let's say that I allow you to have different starting points. Like for example, I give you some set of nodes that you can potentially start from. So maybe this node, and let's say maybe this node, and perhaps maybe let's say this node, right? I don't know. But the point is that like single shortest path says that, okay, if you start at some node, you know, like what's your shortest path to everyone? Okay, but now instead I give you the following. I say, okay, you could have, you could start from multiple nodes. You know, I don't care which node you start from. Let's say you get that for free, okay, but I want you to find the shortest distance it takes for you to get from like possibly any of these nodes to the rest of them now. You know, how should you do it? I mean, the easy way to do things would be, okay, let's just run Dijkstra multiple times, right? For every possible starting point, we'll run Dijkstra once with that node as the source S, right? The thing is that if I had like a lot of nodes, let's say log n nodes or something, right? You need to run that many Dijkstras. So like maybe like log v Dijkstras or whatever, right? Maybe like I have square root of v like nodes that you could possibly use as a starting point. That your algorithm will slow down by a factor of square root of v. Seems very inefficient. Okay, so one way for you to solve this problem, right, is that you should note that like since Dijkstra is a single source algorithm, right, and you know we can't just give it multiple nodes to start. Oh, actually, we can. I'm about to show you how to. But the point is that we can sort of like you can modify the code to do it as well. But like a neat way of seeing it is that you can trick Dijkstra into thinking that it's just a single source, right? So what you do is you construct this one happy node called the source node or the super node, right? And what you want to do is that you just want to draw some edges out such that this source node points to every other node that you could have potentially started from and just give them all an edge weight of 0. So you take the original graph, add this special node, add some edges in, right? And then just let it run. I mean with this new node as your source node. So basically, what we're trying to do here, like basically the idea is that now what Dijkstra's algorithm sees is intuitively kind of that you can sort of like travel to any of these nodes for free, and then like from there you can start like working out like what your shortest path should be. That sort of thing. You know, so this is pretty much all there is to it. Like, yeah, it's a 2-minute presentation. So this algorithm makes sense. It does, right? You should be able to see why it works. Like it's really just, okay, this algorithm can take this edge for free, so when it can, it should, you know, that sort of thing. Yeah. Right. So what's the moral of the story here? The moral of the story here is that sometimes, like, you know, like we've taught you like stuff, right? Like greedy or DP or something, but sometimes you don't have to cook up new algorithms. Sometimes, you know, if you modify your input a bit, or if you just sort of like, you know, you sort of ask yourself, like, this looks very similar to a problem that I solved before. Can I somehow transform my input? You know, can I change my perspective on the problem that I'm trying to solve? Right? Like maybe you can design an algorithm that you know, you can sort of like take existing algorithms and work with them, right? Work with them to come out with new solutions that aren't very new. It's just, you know, like sort of like still useful. Okay, so I have something nice for you guys today. I have some slides from a friend to cover the next topic. And this departs from my usual style because I always whiteboard or I always draw. So let me change the screen from this to this. Okay, so you guys need to let me know. Can you guys see the slides that I'm showing on the screen now? Because I'm a bit afraid that I'm gonna start narrating to myself and then like people tell me like 5 minutes late. Okay, good. So you guys can see it. Okay, cool. So these slides weren't made by me. They were made by my friend Zhijian. You can see his name there. You can drop me an email and say thanks for the slides, for example. I'm very grateful that he let me use his slides. His slides are top tier, top notch actually. Like I think like there was a prof once that saw his slides. Prof that we were teaching for, and the prof was like, "Wow, Zhijian's like champion at making slides." It's like, can you imagine a prof who's good at teaching like tells a TA that like he's champion at making slides? That's like ultimate compliment right there. so I'm excited to use his slides to cover this. I don't think people, unless you've done Harold's like this very specific semester, I don't think you guys would have seen this as well. If you have, then this is just a revision. If not, for most of you, I think this is like one interesting part of algorithm design. So we're moving on from the transform your graph idea, and we're gonna talk about how DFS can solve like some amount of interesting non-zero amount of interesting problems as well. All right. As you can see, this is from like CS3230. So like, why am I covering in 3230? Because, you know, the syllabus wants me to cover graph algorithms. So hey, why the hell not? All right, so let's move on. So let's talk about the 3 problems I want to solve today. So the first problem is finding articulation points. So you should think of an articulation point as a node in a vertex where if I were to remove it, right, I will disconnect the graph. Okay, so let me provide some justification for this. Again, I'm not like a software engineer. I'm not a systems engineer. I'm not a network engineer or anything. I haven't worked in a company before. I've not done an internship. So take what I say with a grain of salt, right? Because it's probably not very true. But you can sort of think of this as like some network that you're trying to disconnect, you know, and you might ask yourself, hey, if I were to remove this node in my network, you know, like, will people still be able to connect to each other, like, you know, in some way? That might be something that you're concerned about. I'm not sure. You know, this like hypothetically in a very abstract scenario, like this is what you would model it as, right? I have some node in my network, and if I were to remove it, will this, you know, maybe in data analytics you would do this, right? Like you have a list of friendships from, like, you know, you have a data set from like Facebook on like friendship links and stuff, and you would ask yourself, you know, maybe this guy is very important, right? If you remove him from the graph, like, you know, like what happens to like the I don't know what people do. Yeah. So a bridge works in a very similar way, but it's for edges now. So you should think of like articulation points and bridges as doing the same thing, right? Articulation point says that, oh, it's a vertex, but if I remove it, I disconnect the graph. Edge is the same thing. So when I say I remove an edge, right, like it just means like I delete this guy, like delete this link, right? Then will the graph be disconnected? Okay. So one thing to note for sure, if I have a bridge, right, these 2 nodes here are definitely articulation points. Okay, but like if I have non-existence of bridges does not imply non-existence of articulation points, right? Because like this, there are no bridges in this graph, but this is clearly an articulation point, right? Okay, so the last problem that we're going to solve is, which I think is far more interesting, is called the SCC problem, the strongly connected component problem. So you can think of this as a directed subgraph. For example, you can think of SCC as a directed subgraph. Sorry, not a directed subgraph, a subgraph, right? Where if I were to sort of partition my tree, my graph, right? So for example, this original graph, I'm going to partition it into the red partition, the green partition, the yellow partition, right? Every node in the same partition can reach each other. Okay, so everything in the red partition can reach each other. There must be some way. You fix 2 nodes in the partition, right? There is going to be some way that they can travel and visit each other. Okay, and if I were to compress these nodes, like these partitions, into a single node, the resultant graph should look like a directed acyclic graph. Right? So I mean, if you just pretend and you squint your eyes, right, like this yellow portion, let's pretend it's a single node. This red portion, let's pretend it's a single node. Then this is clearly a directed acyclic graph, right? Okay, cool. So to solve all these problems, we're going to need to do DFS. Okay, so I hope this should be obvious to you guys by now. But if I were to run a DFS, and let's say that I take in all the edges that my DFS used. In this case here, let's say I have this graph. It's not necessarily directed acyclic, but whatever edges my DFS traverses through, let's just color them yellow for now. These are all the DFS edges that I'm going to be using, right? If I were to put them all together, right, you can prove this is true in your own time, but basically it's going to form a tree. Okay, so you might be wondering why no cycles. Well, you think about how DFS does things, and it doesn't ever visit the same node again. So if it doesn't visit the same nodes again, what that means is that there is no cycle, and if there is no cycle, it has to be a tree, right? And it's actually a spanning tree, but yeah. Anyway, I mean, it's a spanning tree because it has to visit all the nodes or something. I mean, okay, like we're assuming like this graph is like connected or whatever, right? But yeah. Okay, so let's call all these edges that we visit through our DFS as the tree edges. Okay, and then let me talk about the back edges and the cross edges in a bit, because it's gonna be a bit scarier, right? But let me introduce them. So a back edge, right? The way that I'm going to define it in layman terms is that it's going to be an edge that travels back up the same branch, right? So you see these edges in red. I'm not sure if you can see my mouse. I'm not like, but I'm like rubbing my mouse over, like, like running my mouse over the left red edge here. What I'm trying to say is that like this left edge here and like the right red edge here, right? They're back edges because they're like running up the branch, right? So you can sort of see like how there's like this branch on the left and this branch on the right, and a back edge is when it runs back up the same branch. Okay, a cross edge, for example, on the other hand, right? Okay, runs across branches, right? So I think the most obvious one is the one on the bottom right. It runs from the third branch back to the first branch. Okay, so don't worry about like how you're supposed to identify the edges for now. I mean, tree edges should be easy to identify, right? When you run your DFS algorithm, right? Like whatever edges it traverses, okay, color it green. That's definitely a tree edge, right? But you might be worried about how to figure out what's a back edge and what's a cross edge, because it seems that you're going from a visited node to a visited node in either case, right? So how do you tell the difference? As it turns out, I lied a bit. We actually need to modify DFS to actually figure it out. But for now, don't worry about it, okay? Because I still need to introduce a few other concepts. So the first thing is going to be a pre-order number. So if you remember DFS, we have like, I think like from 1 to 3, 1, you should already know this, but there's a pre-order number, there's an in-order number, and there's a post-order number, right? So like right now, the useful one is going to be a pre-order number. So when we traverse our graph, when we do this DFS, right, let's not just do a DFS and take in all the edges, let's actually label them. Okay, so pre-order number is usually the first time you visit a node, right? The first time you ever see it, okay, you give it a number and you do it in an increasing manner, right? So like, for example, if I run a DFS now, the root node starts at 1, then maybe I visit this node, I give it 2, I visit this node, I give it 3, 4, let's say 5, 6, 7, 8, 9, and 10. Okay, so this is my pre-order number. This is one thing that we need, okay? The next thing that we need is a low link number. Okay, now assuming that I already have, I somehow have a way to identify my back edges and my cross edges, okay, my low link number is going to be the smallest pre-order number that I can reach, okay, using only either tree edges or back edges, but not cross edges, okay? I know that's a mouthful. Let me show you what I mean. So for a root node of a tree, let's just give it a loading number of 1 because it's in the tree, right? So it can only either come back to itself or it stays on itself, but then that's just like 1. Okay, so why does node 2 have a loading number of 2? Because if you only look at the green edges and the red edges, right, like no matter which node it visits, right, all of them have a pre-order number that's larger than it, except for itself, besides itself, right? So for that reason, let's just give it 2. I mean, if you take a back edge, you can come back to yourself, but I mean, that's the same thing, right? So that's fine. What about 3? So 3 is interesting. It gets a low link number of 2. The reason why it gets a low link number of 2, you can think of it as taking the 2 green edges on its right and then back up using a back edge, right? So the back edge brings it back up to node 2. And node 2 has a pre-order number of 2, so it has a pre-order number of 2. Okay. Likewise for 4, same thing happens. 5 can't go anywhere, so it has its own number, 5. 6 can go back up using the back edge, so that's a number of 2. Now 7, on the other hand, right, doesn't have a loading number of 2. 7 has a loading number of 7. Because like I said, you can only either use green edges or red edges. You can only either use the tree edges or the back edges. You cannot use cross edges. Cross edges right now are colored with yellow. All right. So even though six can reach like, you know, like 2, right? 7 can't, because we're supposed to discount the cross edges, right? Again, I've not told you how to get them, right? We'll get that in a bit. I just need you to see that these are the numbers that we're trying to get first, okay? And then 8 has, I mean, like 8 can only, you know, reach itself. So like that's 8, 9 can reach 8, right? Using the green and then the red edge. 10 just uses the red edge. So that's going to be, you know, 8 as well, okay? So subsequently, we're going to say pre-U is the pre-order number of U, low U is the loading number of U. This should be all very intuitive. And this is the part where my friend gives you an exercise, except, you know, like we're low on time here because this is meant for a 2-hour tutorial. So I'm going to show you guys how to do it. Okay, so now let's talk about this whole back edge cross edge thing. Okay, what's the intuition here? How do I tell whether something's on the same branch or not? Okay, the intuition that you should have in your mind is that when something, how do I tell when something's in the same branch? It must be the case that the DFS algorithm is still exploring that branch, right? So what I mean by this, I'm not sure if I can draw on Adobe, I don't think, Acrobat Reader, I don't think so. The way to think about this is that when I do a DFS, right, you should think of it as like this DFS. How does DFS look like? It kind of like steps on this node and it sort of like walks down one path until it eventually hits a cycle, right? Then it starts backtracking, right? So it starts walking backwards until it can find like something new that it hasn't seen before, then continue along that path, right? So I mean, like for example, let me see if I can get the numbers out. So like from 1, let's say it steps onto 2, it walks onto 3, it walks onto 4, it steps onto 5. Now from 5, it can't go anywhere, right? So it walks backwards, right? It walks back to 4. And after 4, it says, okay, is there anything else that hasn't been visited? Then you would see 6, right? Like this node here. Then you would say, okay, let's go here. Okay. Now when 6 goes to 2, right? And then 2 has been visited. So 6 technically has nowhere to go. It should start walking backwards, right? And where would it go after that? It would walk backwards all the way back up to the root. And then it will come back down to node 7, right? And it will say, okay, 7 hasn't been visited, let's go to 7, right? Then 7 sees, oh, you know, I could technically go to 6, but 6 has been visited, so I shouldn't go there anymore, that sort of thing, right? So this is how original Dijkstra works, right? I mean, that original DFS works, right? So how do we work in the numbers? So you should think of it as when I'm still sort of, when I haven't backtracked past, like when I haven't backtracked away from that node yet, I'm still technically exploring it. I'm still exploring what it has to offer me. Right? So this is different from being visited, right? The moment you step on a node, it's a visited node. You should not step on it again, okay? But when you step on a node for the first time, right, you're still exploring it, right? So you need to remember 2 things in your DFS now instead of just 1. You need to remember when you visit the node, this is so that you don't step on the same node again, right? And the second thing you need to remember is when you're still exploring that node, right? So in this case, right, when I travel down to 2, right, I'm still exploring it. So I actually shouldn't be giving this number yet. So let me just lay out all the numbers, because the way that we're labeling it is actually different from how it's shown on the slides. So just bear with me here. Like the idea is going to be that you move from like node 1, and you DFS all the way down to like 2, for example, to 3, to 4, 5. Nothing interesting here, right? But when you hit node 6, right, okay, you're going to ask node 2, like this node 2 again. And remember, all these loading numbers have not been filled in yet from the perspective of the algorithm, right? What's going to happen is that node 6 is going to ask node 2, have you been visited? You know, then node 2 will say, yeah, I've been visited, right? Then you know that the DFS algorithm won't step on it again. That's fine. But how do we know it's a back edge? You're going to ask node 2, are you still being explored? Okay, and node 2 is going to say yes. So if you're still being explored, right, that means you're still on the same branch, right? So you say, okay, this is a small number, like 2. Okay, I'll fix it at 2. That's the only that's my loading number, right? So what happens is that you're going to backtrack, right? So 6 was technically still being explored as well, and then now when you move away from 6, you would say, okay, 6, you're done being explored. If anyone asks you, you're going to say, I've been explored, right? You know, like I have been explored. No one's exploring me anymore, so like that's it. And then you move back up to node 4, right? Now 4 has 2 loading numbers to deal with. It's either loading number of 2 or loading number of 5, right? Since we want the smallest one, we should be taking 2. So then node 4 says, okay, my loading number is 2. Likewise for node 3, nothing interesting here. It only has 1 child. The child says I have a loading number of 2, so my loading, so 3 will say, okay, since you could reach 2, I can reach you, so I can reach 2. Hey, that rhymes. But anyway, we move back up to 2, okay, and 2 kind of says, okay, you know, I've looked at everyone, and the best loading number they could hit was 2. That's myself, so I'm going to set 2 as my loading number as well. Okay. Now remember that every time I backtrack and move back up the DFS tree, right? I actually have to mark the node and saying, okay, I'm done being explored. So when the DFS algorithm leaves this node, right, and it comes back up to the node, and it goes back down to 7, right? And when it goes down to 7, because 7 hasn't been visited before, so it goes down to 7, right? By this point in time, right, 2 should say something like, I've already been explored, you know, I've been visited and I have been explored, like no more. The DFS algorithm isn't sitting on my node anymore, right? So likewise for like 3, 4, 5, and 6, right? So now the node is here. Now the DFS algorithm is here, and it looks at this node, right? And it says, hey, 6, you know, like, have you been visited? Then 6 should reply, yes, I've been visited. So the DFS algorithm knows not to stand on it anymore. Then it will ask the second question, have you been explored, right? Then 6 will say, yeah, and I'm done. Like, you know, the DFS algorithm isn't on me anymore, right? So when it says that, you know that you're not on the same branch, right? The algorithm must have went further back up and then come back down to you. So it's not on the same branch. So whatever low link number it has, you can't take it. Okay, so that's the only neighbor that this node has. So, you know, too bad for it. It has to have a low link number of 7. That's its own low link number, right? And if you work out the rest of the algorithm, like that's pretty much how it should look like. Okay. Why is it 5, 5 instead of 5, 2? Because there is no edge going out of 5, right? Does it make sense? Cool. Okay, so with this in mind, this is how we're going to color, like, I'm not gonna say color our graph, but this is how we're going to label our graph. Okay, and based on this labeling, we actually can solve all 3 problems already. It's like a 3-in-1. Okay, so let's move on to bridge detection. Okay, actually, let me talk about this. So what's the intuition behind this? Why are we doing this low link idea? Okay, so the reason why I want to do this is because you should think of your low link number, right, as the furthest up the tree you can travel. Okay. Intuitively, what I'm trying to say is that if I were to run a DFS algorithm, like if I were to somehow traverse and do this walk, right? Okay, like how far back up the DFS tree can I escape to? Right. So like, for example, let's say from 3, I know that, like, you know, like I definitely have a way to walk all the way back up to 2, right? Like from here, there is definitely a way for me to sort of like step back up to 2. Okay, like from 5, I know I can go anywhere. I mean, like, okay, we'll do the 7 case later, but anyway, right? That's kind of the point I'm trying to make. Okay, so fine. So with this intuition, you should sort of think of bridge, right, as when if I have an edge that looks like a bridge, right? There's going to be a bottleneck somewhere, right? And that bottleneck means I can't go further back up the DFS tree, as you're going to see. Okay, so what do we do? So if I tell you I want to detect bridges, okay, I want to list out bridges where all the bridges are, where all the edges are bridges, right? So, and I tell you runtime over v plus e. So you would say, okay, fine, we're going to run this special DFS algorithm that tags like the low link and the pre-order numbers, right? Run this same algorithm that we did. You should get some numbers like these. They're not unique, by the way. Depending on how your DFS algorithm works, you might get different numbers. But the whole point is that, like, these numbers will always satisfy the nice properties. So what's going to happen is that, okay, wait, let's see. Let's run for the red. Okay, so the observation that you should make here is that UV is a bridge, edge. If the low link number, right, the low link number for what you're pointing to is larger than your pre-number, your pre-number. So remember your pre-number, right? Like, for example, if you look at this edge from this node to this node, right? This edge is a bridge because this guy's pre-order number is 2, but this guy's low link number is 3, right? So what does this tell you? This tells you, right, that like if you ran a DFS starting from this node, okay, and you ran it in the way that, like, you know, like it starts walking in the same direction that the original DFS algorithm did, right? The best that it can do is only come back to itself, and it can't go back any further. Does it make sense? Right? So what this tells you, right, is that, okay, you know, if I start here and I start walking down this tree, if I can't go back up any further, what this means is that there must have been, like, you know, definitely no path, right, that escapes me, right? If I start from here and I start walking anywhere, I'm just gonna come back to myself. That's why my loading number is 3, right? So if this guy's pre-order number is 2, this means that, you know, you can think of it as a timer, right? Like I can't escape to a part of the DFS that was earlier than me, right? So this tells you that this is a bridge edge, right? Likewise for the rest of them, if you look at it, you should see it that way. It's kind of like, okay, I start this timer is going to keep track of like the first time that I reach a node, and if I look at the earliest time that this guy can reach, it's a time later than me, which means that it can't go back to a time before me, right? So it can't escape me. So this guy is a bridge edge. So all you have to do is run the DFS algorithm, then iterate through all the edges, right? And as long as it satisfies this condition, you just throw it into a list and say it's a bridge. So OV plus E time, that's still OV plus E. Cool. So a very similar observation works for articulation point, right? So if I tell you, find all the articulation points, OV plus E time, you should think along the same lines. Okay, let's just run this special DFS algorithm that we have right now. Okay, and then the observation to make here is that if you're the root of a DFS tree and your okay, this is a special case, but yeah. So if you're the root node of a DFS tree and your degree is larger than 1 in the DFS tree, right? What that means is that if you had degree larger than 1, definitely what you are an articulation point, because there was no way for you to go from one of your children to like a different to one of your to one of its siblings. In the case here, we don't have that, right? But like the point is that if, like, for example, this edge, this bottom edge of the triangle was not there, then this you would have a the degree would be greater than 1, then this guy will be the root node will be an articulation point, right? But that's not the interesting case. That's not an interesting case. So what you should look at is that, like, for example, this case, this node here, 6, 1, right? So what 6, 1 tells you is that sorry, it's like 6, 1 versus the rest of the nodes, right? So you look at all its neighbors, right? And you would see that, for example, the low link number here, wait, what am I supposed to be looking at? Okay, yeah. So the low link number here is like larger than or equals to the pre-order number here, right? So for example, yeah. So the low link number on 6 here is like here 6 as well. So what does it tell you? What does it tell you? That tells you that, like, you're only going to come back to yourself, right? So again, you can't escape this node, and if you can't escape this node, that tells you that it's an articulation point, right? So it's a very similar observation to the bridge edges, basically. But I think there's like an equals there, because, like, yeah, you can hit your own node or something like that. So yeah, you should that's how you should be seeing it. I think the intuition works well for like both problems. Okay, so this is pretty much how you solve bridge and articulation point. But the cooler one is, okay, this is an exercise, let's skip that. The cooler one is the strongly connected components. Okay, so let me just quickly like finish this, then we can all call it a day. So strongly connected components, what I want is I'll give you a directed graph, right? Not necessarily acyclic. I need you to list all components, right? So like I mentioned, the way that you think about connected components is that a sub portion of a subgraph is a connected component if, like, like from one part of the graph, I can somehow reach one part of this component. There exists a path for me to reach other components, right? Sorry, another node in the same component. Okay, this does not mean it's complete, right? Like, I'm not saying that there is an edge. I'm saying that there is a path. So a path may require more than one edge, right? Okay. So what we're gonna do is, what you need to observe here is that for any strongly connected component, right, there must be some node, okay, that appears. So there is some node U such that all vertices in SEC appear in U subtree. Yeah. So like basically, you should think of it as, if I were to look at the subtree, right, there must be some node that's going to be a root, and all the other nodes in the component are in its subtree. I'm not saying everything in the subtree is in its component, but I'm saying everything in the component is in the subtree, right? Those are two different statements, because you see 5 is in the subtree, but it's not in the component, but everything in the component is in the subtree. Okay, so the root, right? Like let's just look at the root. Okay, the observation here is going to be that if I'm the root of a strongly connected component, okay, then my low order my low link number is the same as my pre-order number. So in this case, right, what's going to happen is that 2 here is going to be a root, right? 7 7 here is going to be a root. 8 8 here is going to be a root. 5 5 here is going to be a root. 1 1 here is going to be a root. Okay, so intuitively, what you should be doing is you should sort of be like you should sort of like be grouping these together based on those nodes, right? So I don't really quite get this part, but anyway, like so this apparently is called Tarjan's algorithm. So let's say you already have all the pre-order and low link numbers, okay. So the way that you're gonna do it is that we're going to try to like group all these nodes together. Okay, so the way that we're gonna do it is that we're going to perform a DFS, and then what we're gonna do is that we're going to sort of like pop out the nodes and partition them together. So my friend had this like very nice animation for it. Let's say that we already did the DFS, we already did the tagging and stuff. Now we start at this node, we sort of like traverse along this tree again, we see 5 is like node 10 here has like tag of 5 right? So we know that it's its own root. So what we do is we just pop it out as itself, right? Move back up the DFS, move back down here, right? And then what's gonna happen is that the DFS here is gonna see like 2 2. It's actually gonna not yet, sorry. There's gonna now there's no neighbor, so it goes back up the DFS tree, right? And then when it sees 2 2, what it knows is that everything here has the same what's the word? It's part of the same tree, right? So what it does is that it pops everything out here. Okay, it pops everything out until 6 because 6 has the same loading number, right? As 2 2. And then it's just basically gonna put that in the same partition, so on and so forth, right? It sees 1, then you see 7 7, then you basically just put that on its own own partition, do the same thing here, add all these into the stack, move back up again. And once you see 8 8, you should be popping everything from the stack and everything that has loading number 8, right? So in this case, it should be like 9 7 and 4, right? So you move that out into the same set, right? Go back up to 1 and then just basically put that all together. Okay, so like these are basically your strongly connected components. The guarantee here is that if I were to start like at some take any 2 nodes, like for example 2 and 6, there must be some way for me to reach for 6 to reach 2 and for 2 to reach 6, right? And if I give you, for example, the like 4 and 7, there must be some way for you to reach there must be some way for 4 to reach 9 and some way for 9 to reach 4, for example. Okay, so this is what we want. And then, like for example, you can think of this as a condensation graph. So sorry. So then from this you can build a condensation graph, which is to say that you can like compress all these nodes into like a single. If you compress like all these components into a single node, the resulted graph is what we call a condensation graph, which is also a DAG. You can think about why that's the case. All right. So with this class is technically over, in case you might like, let me just say a few more words, you know, like in case you might be wondering why we would ever need this. The full answer is, like, to be very honest with you, I'm not very sure, because it's not as if I've actually solved any real world problems using this. You know, you could think of like maybe like some project management like scenario where like, oh, if you have a cycle in this graph, you know, it kind of says that like you should be working on these tasks in parallel, and then you can sort of like try to dagify this graph a bit and see like, you know, overall what the picture looks like. Yeah, I don't know. It's still a really cool problem, I think, and it can be solved using DFS instead of like any funny like weird tricks. But yeah, so that's all I have for you guys. Yeah, I don't know. There's nothing else to say. I will see you guys next week then. I actually have like other graph problems, but I'll post them in Telegram, and then we can have a discussion there. Okay. If not, class is over. I'll stay around for a few more questions in case you guys have any. No worries. Okay, let's see. No worries. Is this the same as finding cycles in the graph, actually? What do you mean by finding cycles in the graph? Could you elaborate on that question? We're doing a bit more, right? Because if you want to find a cycle in the graph, for example, all you need to do is okay, like finding cycles in a directed graph. Okay, so are strongly connected components equals the cycles? Yes, right? Because you know that, for example, okay, so like I take any 2 nodes. Okay, so as long as my strongly okay, I can't say our strongly connected components equals the cycles, because you could have a strongly connected component of size 1 for every node, right? So I could give you like, for example, 500 nodes and you have 500 strongly connected components. That tells you it's a DAG, right? But if I had non-trivially sized strongly connected components, are they cycles? Yes, right? Because what was the guarantee? The guarantee is I give you any 2 nodes, I can like nodes U and V in the same SEC, right? Node U can reach node V and node V can reach node U. So what does it tell you? That tells you that node V can go to node U and from node U you can go back to node V, right? So that there exist cycles, right? So you like one contrived justification you could imagine for this would be, I have a graph with possibly negative weighted edges, and you know, you might be wondering, should I or could I run topo sort and do a 1 pass by 1 fault, right? And then And then, we tell you, oh, if this is a DAG, you can topo sort and run one pass, right? One pass by one fault, right? So that would take OV plus E time to find shortest paths. So, very nice. But then we've never, I don't think we've ever taught you how to decide whether a graph is directed acyclic or not, right? So yeah, you're right. So you can just run this algorithm, right? Then look for all the strongly connected components and see whether all the SECs are of size 1 or not, right? Because if they're not of size 1, then you would say, oh, it's cyclic. Okay, I there is no way I can run tuple sort and do one pass Bellman font. Then maybe I should consider just using like normal Bellman font, right? Though I think there are tuple sort algorithms that already not just work assuming there is a DAG, but actually if it's not a DAG, it should tell you that it's not a DAG. I'm pretty sure. I think Khan's algorithm should do that for you anyway. So you don't actually have to run this. But yeah, it's a cool observation. It's a good observation. No worries. Any more questions? This is so weird. It's like, class is over, right? People are still like just hanging around. I'm just like, like yesterday during midterms, like even though it was past 12, people were still sitting in, and I'm just like, why are you guys here? Exam is over. Okay, so if someone's leaving, I'm gonna leave. Like, yeah, I need to get back to work. Okay. Again, I'm gonna post some questions on chat, so you guys just like have a look see there if you need to. All right, I'm gonna go. Bye bye.